Hi everyone, it's me Marivel. So for this video, I'm going to discuss about the three mathematicians that I've choose, who are Johannes Kepler, Isaac Newton, and Thomas Bayes. Johannes Kepler was a gifted geometer who applied his mathematical abilities to solidify our understanding of the solar system. Kepler worked closely with the great empirical astronomer Tycho Brahe, who kept some of the most meticulous records of the movements of the planets up until that time. By analyzing those records, Kepler was able to confirm and refine the Copernican view of the solar system. The planets move around the sun, and the time it takes a planet to move around the sun is described by precisely defined mathematical laws based on the shape of the planet's elliptical orbit. Kepler's laws are impressive because they are precise and elegant mathematical description of a physical process. The fact that things in the world like planets orbiting the sun follow such laws has been referred to quite elegantly by 20th century physicist Eugen Wigner as the unreasonable effectiveness of mathematics. Kepler's laws are an early example of that unreasonable effectiveness. Kepler's laws also set the stage for Newton's development of his laws of motion and especially for his theory of gravity. Kepler's contributions to our understanding of planetary mechanics lead to his being the namesake of NASA's first space probe that was dedicated to searching for planets outside our solar system. Next is Isaac Newton. No less of great mathematician could be complete without Newton, with his invention of calculus, an achievement shared with our next entry. Mathematics was able for the first time to systematically describe how things change across space and time. Newton developed calculus in the context of developing his theories of physics. The language of calculus is the most natural way to describe motion. A car's speed is the rate at which it is changing position, or the derivative of its position. The acceleration of a ball dropped from a tall building is in turn the rate at which its speed is changing, or derivative of its speed. And Newton understood that this acceleration was the result of the force of the earth, gravity acting on the mass of the ball. Newton's physics also represented a milestone in our overall view of the world. Earlier, physicists and astronomers, like the previously mentioned Johannes Kepler, understood that the behavior and movement of objects followed certain patterns. But Newton and the physicists who would follow him understood, with the help of the mathematics, the reasons why objects follow those patterns. Further, Newton's laws were understood to be universal. The same force of gravity that causes a ball to accelerate as it falls is the force that keeps the moon going around the earth. The idea that the same laws of physics apply everywhere in the universe is a core tenet of science, and it is supported by all existing evidence. Next mathematician is Johannes Bayes, provided one of the most important tools used in probability theory and statistics. It allows us to figure out how likely something is based on the evidence we have at hand. Finding the probability of an event when we have a good understanding of the underlying mechanism tends to be pretty straightforward. Some basic calculations can give you the probability of drawing a full house in a hand of poker, or getting 5 heads in a row when flipping a coin 5 times, or of holding a winning lottery ticket. In most interesting situations, however, we are interested in the reverse problem rather than computing probabilities of outcomes based on a known underlying mechanism. We want to gain an understanding of a hidden process based on observed outcomes. This need to understand a hidden process based on observations underlies situations ranging from medicine. How likely is it a patient has a disease based on a positive test result for that disease? To the social sciences, what is the best model that explains the relationship between inflation and unemployment based on historical observations? So Bayes' theorem gives us a formal tool that allows us to answer this question. The theorem lets us calculate the probability that a particular Bayes' theorem gives us a formal tool that allows us to answer these questions. The theorem let us calculate the probability that a particular underlying process is happening, given our observed outcome based on our understanding of the likelihoods of getting our observed outcome in two cases where our underlying process is true and where it is not true, along with our prior degree of faith in the underlying process. Bayes' theorem is an incredible powerful tool in analyzing information to get at the reasons for why that information looks way it does, and it is also the underlying framework for an entire school of thought in statistics. And that's all, thank you.